All right, so I guess it's time for our first tutorial today. Thank you, Greg, for the introduction. Like you said, my name is Aaron Saxton. I'm the data scientist for the Blue Waters Project Office. So data science has a very broad umbrella. The things I am most interested in are machine learning algorithms. In particular, because I'm part of a HPC community now, I am most interested in distributed training. So whatever algorithm you have, how do we chop it up and evolve its weights and its biases to get a good model out of it. The one problem I've found so far that lends itself to HPC is deep neural networks, convolutional neural networks used for image feature detection. I'm not necessarily attached to that problem. In this particular presentation, I won't go into it very much. But that's kind of the background that I'm coming from here. So let's see, will that work? No, that doesn't work. This work? That works. Okay, so today, distributed training. With machine learning, that's a very, and AI and statistical learning and all that kind of thing, that's a super, super broad topic. A lot of different things out there. You have supervised learning, unsupervised learning. You have a whole garden of techniques, random forest, just traditional neural networks, autoencoders, k-means, blah, 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 blah. Some of them might lend themselves to HPC. The only ones that I've found so far are the deep neural networks. So this is an example of a supervised learning technique, meaning that in your studies, you've found some data set that you think is a good pedagogical, well, from a machine's perspective, a good pedagogical source of information, but you as a human glancing at it can't quite dig it out. So the first and by far the most computational intensive part of this process is using that data to do supervised learning and train your model. Once you've trained your model, you can run the inference on Blue Waters, but it probably makes more sense to bring it back down to your laptop or give it to your graduate students and do whatever analysis you want with it. Go apply it to some other data that you're interested in. Okay, so the tools we have on Blue Waters to perform distributed training, we have TensorFlow 1.3 out of the box. Okay. That means that Colin, who'll be talking a little bit later, has gone and made sure that this thing runs efficiently on the Blue Waters hardware, but the actual API is basically what you're going to read on the TensorFlow documentation. So just go to tensorflow.com and look up distributed training, and it's going to tell you about a whole bunch of features that team has built for doing distributed training. It's not very good. Kind of sucks. But because that's what the community knows, I at least wanted to make it available. And also, that's what I've been investigating the last roughly 9 months I've been here, and came to the conclusion I don't like this very much. We have just been given, so we'll talk about TensorFlow 1.3, out of the box usage. Then we have 1.3 with Cray's machine learning plugin. This thing's super neat. So the out of the box does not use MPI, and it uses TCP over the Gemini interconnect, which I've been told and have experienced is slow and bad. The Cray ML plugin gets rid of a lot of the formalisms that the out of the box usage has, and implements the parameter sharing over native MPI. So much faster, and it has a couple other pieces of secret sauce that we'll talk about today of why it's so neat. And there is some neat features going on there. So I was talking to some of you at lunch yesterday, the day before, and all your colleagues are saying, oh, TensorFlow is so last year. It kind of is. PyTorch is another tool we provide on Blue Waters if you want to do some distributed training, and I'll walk through. Now, PyTorch is something I've been working with and developing with. Unfortunately, I don't have hardened code examples for it yet. I am going to run through some of my experimental code to kind of show you what the major components are and show you where you can find those examples once they are hardened. Is there a question?
All these tutorials, is this material accessible on the web?
So,
I don't have to type that link in.
correct. Yes, that's accessible. Oh, I'm sorry.
No, I meant the slides you're showing and everybody's showing. Are they accessible on the web?
I've been told they're going to be,
Okay.
but
So with the tutorial, this is just kind of watch and listen. There's no way to do anything.
at the moment, correct. Yep. And I have 20 more minutes, so or no, 25 more minutes. I would like it to be more like that. I am going to point you to some GitHub repos that you can clone in your user space on Blue Waters and run some of this stuff. Not necessarily live right now, but after the fact. Okay. Going back to distributed training, one detail I forgot to talk about. If you want to know more about machine learning in general and convolutional neural networks, I've been doing a series of webinars that I think I spend 3 hours going through it and really kind of showing you some resources. So I'm going to skim over all those nitty-gritty details and just tell you how do you actually put your fingers on this code on Blue Waters. 3 packages. TensorFlow out of the box, TensorFlow with Cray machine learning plugin, which is really neat, and then PyTorch, which is sort of up and coming. My colleagues told me that the actual Torch project's been around for a long time, but the Python implementation is relatively new. And then we are trying to support some data resources on Blue Waters. So if you just want to go monkey around, or if you think your problem is very, very similar to an image classification problem, I've been working with the ImageNet data, which has been attributed to this big eruption of success in image processing technology in the last 5 years or so. So on Blue Waters, we do have a set of ImageNet data that you can take and process and feed into your neural networks. So you don't have to go through that download process yourself. Me and other team members are interested in making this example training data repository more extensive. So you guys don't have to go through the pain of downloading and massaging and keeping it on Blue Waters. Okay, so that's what we're going to get through today, if I can talk fast enough. Oops. This one? There we go. Distributed training. So a brief, or a training life cycle. So this is typical stochastic gradient descent. You take a batch of input. This is your training data. So this is an input data that a human or some process, maybe an auxiliary expensive sensor, something has gone and said, this data has this kind of classification. You take a batch of it. With my ImageNet stuff, 32 images is about what you can fit in a GPU at any given time. So a batch of 32 items. You feed it forward through the model. So you've gone and decided which particular machine learning model you want. You take that input, you feed it through, you look, you initialize it. If you're the more advanced techniques, you have some knowledge about how to initialize it a priori. You feed your data through and you get an output. First time you do it, it's probably going to be bad. It's probably going to be really bad. You're going to put an image of a cat in the top, and it's going to return the classification of a pond. That's crap. Okay. So you feed it forward, and you get this wrong output, and you compute the loss. You say it should have been a cat, but it was actually, a pond, and you have some loss metric, root mean squared or cross entropy, and you say it's that much wrong. When you compute the when you compute the loss, you then do a back propagation. Back propagation is basically calculus 1 chain rule, or some variant of it. And that's what gives you the gradients. You use the gradients to advance the trainable parameters. So you initialize it. It was probably a bad initialization. You feed a batch through, loss, gradient, or back propagation, gradients, and then you say, OK, let's go wiggle all the weights a little bit. And repeat. You do this over and over and over again. The thing that makes this stochastic gradient descent is that on your training set, you're only you're taking either one example or a batch of examples and walking through one round of your training data. And so getting through all your training data is called an epic. Okay. So Data parallel distributed training. So the, the philosophy here is you take your model, you copy it across all your workers, all your nodes, and each worker gets a different batch of your training data. So each worker is going to do the feed-forward, backpropagation, gradients, and they're all going to get slightly different gradients. Kind of hope they're maybe in the same direction, but they don't have to be. And that's where you start sharing. Let's see, what did I say there? Share and aggregate. Lots of different techniques to aggregate. Just then, first naive thing to think about is maybe do an all reduce. So you do an all reduce, each worker finishes calculating its gradients. Before it actually updates the model, it says all reduce sum, and adds it all together. You can do a sum or an average, depending on how you like to weight your, excuse me, how you like to weight your learning rate. So share gradients and aggregate. And then once you have the gradients, the aggregated gradients on each of the workers, if you've written your code right, they're all the same. So everybody then advances their model a little bit, the same amount. And then you do the process again. Okay, so bucket of distributed training features. My experience, there isn't a good taxonomy of all these kinds of things. People are mixing them, thank you. People are mixing and matching these techniques. The TensorFlow out of the box is parameter server worker. So you have a host, one of your Blue Waters nodes, that just sits there and keeps tracks of the parameters. And then you have a whole bunch of workers. You have multiples. You can split up, you can take all the trainable parameters in your model and split them up across multiple hosts. And then in addition, you have multiple workers doing the feed forward, backpropagation, and gradients, and then pushing them back to the parameter servers. This winds up being a bad way of doing things on Blue Waters, but it's the lowest hanging fruit. You can do this synchronous or asynchronous. You can just let each worker process batches, update its own gradients, and aggregate them only when they have time to. Most recent research suggests that synchronous training, even though you have a period where you might be waiting for other workers to finish up, wind up give you better convergence results. The verdict is still out whether you want to try and process more data faster or be better about keeping your model up to date. That's still research. There's also something called PerApp. PerApp is kind of a mixture, the result of PerApp is a little bit of a mixture of synchronous and asynchronous. As you're feeding forward and doing backpropagation, you're simultaneously asynchronously sharing parameters. On Blue Waters, it happens that things keep up to date pretty friggin' well. So it virtually is synchronous, but yes, things can get out of date a little bit. People implement PerApp with native TensorFlow ops. A colleague of mine who did that says it doesn't scale very well. That's part of the secret sauce that the Create ML plugin is doing for us, is they fix that problem. And all reduce. That's basically what I described a moment ago. So those are all the different things. There's variants on all reduce where you can kind of do it asynchronously. Okay. So TensorFlows, so I've been saying a lot of words, but to help you understand this better, a little bit of a diagram here. So TensorFlow's native parameter server worker distributed training model is, let's see, I hit the right one. Okay, so we have parameter devices here. Let's think of that this is one particular parameter. This diagram doesn't show it, but you can have many of these parameter devices tiled here to help distribute the load of sharing all these things together. So each device says, "Oh, ask the parameter server, what's my state of trainable parameters? Each device has the graph of the model, so it knows where to put those and how to move data through it. And it takes a batch of data. Each one of these gets a different batch of data. Passes it forward through the model, backpropagation, gradients, delta p, the gradient of that parameter. Sends back to the parameter server. Parameter server adds it and updates it. So these guys here are usually doing GPU type operations, doing kind of doing GPU operations. The update winds up not needing that. Okay. So synchronous means that you add it all up and then you update. Asynchronous means that you're getting the parameter whenever the particular worker is available, updating the parameter, and then whenever the model is asking for to say, oh, I'm ready for my next step, then it's reading from the parameter server and getting it. Okay. PerApp, this is, okay. So for those of you who've read some of this, this winds up being, some of the literature, this winds up being the model graph of Inception version 3. So that was one of the Google well-performing models. The inputs are on the left. The output is out over here on the right. And so as you're doing your feed forward and computing the results of each layer, there is some type of network sharing, whether it's MPI or something else, that's updating the model parameters as it's feeding the data through. So this is called PerApp. If you wanted to implement this in actual TensorFlow, you would say, I have a linear layer op, then I have a all-reduce op, then I have another linear layer op. And so as you're feeding data through here, it's doing parameter sharing. And then all-reduce. So you have model gradients, you feed forward, backpropagation, gradients, and then you do all-reduce sum. You can also do all-reduce sum and then divide by your ranks to do an average. That detail is about how you like to do your learning rates. And I'm not sure if I'll have time to talk about that too much today. Okay, so that was the background. So what do we give you? I've been maintaining this GitHub repo, and it currently is under my name, A. Saxton. The repo is called NCSA Blue Waters TensorFlow. These are boilerplate examples about how you can do an example end-to-end run of this kind of material. So I have so the two big things. There's some other details in here that I'll get to. Data sets. So each data set usually has its own little hiccups and gotchas about how exactly you want to process it. I've gone and imported and modified some code so that you can build the ImageNet data set to use with TensorFlow. I'll take you through an example of that in a second. And then run scripts. These are the top of the stack. They have a couple of little gotchas, so that's where I'm going to start. But in principle, the things in here should be as simple as possible. They should just be calling the main function and kicking it off. So I'm going to show you what's going on there. And then I didn't highlight it yet, but the actual meat of everything will be in here, and we'll discover what's going on there. Whoops. Okay, so the first task, I'm not going to go into this too much today, is prep your data. And these, so underneath the ImageNet, underneath datasets ImageNet, I have a script that extracts data from an archive. This is the data that we host on Blue Waters for you to get to, and I'll talk about more about how to get access to that in a little bit. But this goes and says, oh, you want to only train on all the classifications of cars and streets. Okay, you go modify one of these files, run the script. It'll extract only the things that, only the images that are cars and streets. And then you say, okay, now of all those cars and streets, I need to actually turn it into data that TensorFlow can read. Then you run your build ImageNet data. Pretty simple. I've been debugging it for a while. So it was pretty stable at this point. So if you're having trouble, please ask me, and I can probably point you in the right direction pretty quick. Okay, so once you extract your data, this is the meat of it. This is the thing I want to get to and start talking about a little more. You actually run your training. I give you an example of a run script that sets everything up correctly. It has a couple of, whoops, too many, there we go. It has a couple of novel features. One thing I said earlier was that the worker nodes with out of the box TensorFlow are the things that are doing most of the GPU computation. And the parameter servers really aren't. They're mostly just being hosts, listening and kicking back out and doing some lightweight arithmetic. So a novel idea, Blue Waters has a feature where you can split your job between XE and XK nodes. This is an example of how to manage that. You don't have to, though. I've written all this general enough that if you just said, I don't want to mess with that, I just want 10 nodes. The way I have it default coded, 2 of them will go to, a quarter of them, in this case 2 of them will go to parameter servers, and the other 8 will go to workers. Wall time about 10 hours. It just depends on how the problem you're trying to solve. And so forth. This is all smarts I put in there to make sure that you can run these on mixed XK, XE jobs, or just all on XK. Yeah, there we go. Yep.
Is that checkpoint or the job needs to start and finish?
It's it does checkpoint. In fact, while developing, I get annoyed that I restart a job and I forget to delete the checkpoint, so it reads the checkpoint. So I kept this in here just in case you're doing development, and I uncomment this out. Okay, so let's see. I will show you that in a second. A number of steps. The native way I've been doing this is just, controlling when to stop the model by how many batches of data it processes. Mini batch size 32, learning rate. I've tried to squeeze this topic in here. Come talk to me about this afterward. AP logs, so forth. Checkpoint directory. So TensorFlow does set up all the checkpointing for you. And that, as much as I'm kind of poo-pooing TensorFlow, it does have a lot of nice features. And I hope to summarize those in a little bit. It does have a lot of nice features. One of them is just native checkpointing. Okay, need to move forward faster. This is the actual run command. And the thing that it's calling is a Python script. Big surprise. And that's the theme of these talks is Python. ImageNet inception, blah, blah, blah. So data directory, I'll show you where that is in a moment. Number of steps, checkpoint directory, there you go. And AP run, and it does a mixed XK, XE job. If you allocate only XK nodes, all this other fanciness in here will work out of the box, no problem. Okay, I don't think I put the code examples here. All right, so in that Python file, or in that Python script, this is the basic program structure. Set up the TensorFlow parameter server worker, begin data load queue, define optimizer, define model inference, define loss, add compute gradients to the TensorFlow graph, and then begin your loop, your training loop. So let's actually go look at that. Let's see if I can hop over there easily. Okay, so this is it. So I'm on a laptop I'm not used to. We'll see how this goes. So as we saw in the previous slide, the top of the stack, or the top of the Python stack, is in BW distributed train. In here, I'm showing you an example of Inception. I have implemented AlexNet and ResNet 50. If you wanted to play around with those examples are in there too. Inception. Okay. Thank you. So basically everything, the top level function is Inception distributed train from about here all the way down to here is the annoying TensorFlow specifics about setting up your training cluster. If you want to build your own model and do all that, I suggest you come here and copy this code over. I wrote it as a boilerplate style, so for pedagogical reasons, not because I'm a bad programmer, just so you can kind of see where this stuff is. So here is then where we start importing the data, splitting. This is what makes it data parallel. Here's where we start. Whoops. Here's where we start defining the optimizer. You'll notice I have a couple of other optimizers commented out. The momentum optimizer is one of the more traditional ones to use. However, the paper that came out last year about training ImageNet in 15 minutes, that's what this guy is doing. So yeah, momentum is one of the more traditional ones, but RMS is where all the latest breakthroughs have been happening. So then down here is where the actual the loss is defined. In this particular case, I used cross entropy. Oops, where did I do that? Oh, Inception is a little bit weird. It has some auxiliary outputs that you want to, that you also do a cross entropy max and sum them up. So this is an example how you can start adding up all the losses however you want. And that's part of the research, that's part of the fiddling, the human getting in there. It has stop hook, or it has training hooks. This is where the training actually starts. This monitored training session is where it actually goes and starts hooking up all the connections and setting up the parameter servers and initializing everything. While should stop. Oops, come on. This is the training loop. And monitored session.run, train ops, train loss, global step. Or whoops, train ops, train loss. This will invoke all the optimizers and advancing the model. So with all that, the reason I wanted to walk through that is, okay, that was big and complicated, and oh my goodness, how am I ever going to do that? Well, you're going to walk through all the TensorFlow distributed training documentation, and they'll explain exactly what you're seeing up there. On the other hand, let's say you want to use the fancy Cray ML plugin. You import MLCom, or MLCom. Let's see, can I do control find MC dot? You initialize it. Initialization, because it's all MPI based and it's very, very close to the hardware, you need to know the actual memory footprint. So there's in line 118, there's a little calculation about how you build that. You need to set up what's called a session run hook. So during the monitored session, while you're doing your while loop and testing to see if you should stop, the monitored training session will say, oh, do you have anything special you want to do? And this is what the session run hook is, and it's what actually performs the broadcast. And it's doing it asynchronously, and it's doing PerApp. And here's where you actually tell the plugin, oh, here are the gradients that TensorFlow just calculated. And during your run hook, go do the right thing with them. And then finalize. Okay, so I think I'm out of time, which saves me a little bit of embarrassment because the PyTorch code I haven't hardened. But it's basically as simple as this the CRAML plugin. It's go do your training the way you normally would, ingest data, forward, backward, define the graph the way you normally would with a PyTorch model, and then do an all reduce. And it's much lower hanging fruit than going through and doing the parameter server worker for TensorFlow.